Hello, in this video we will present blockchain-based federated learning environment and data marketplace demo by FBK and IBM. We assume the viewer is familiar with the blockchain technology and its basic concepts. So what is federated learning? Federated learning is an emerging approach that aims at establishing cooperation between a group of agents for the solution of machine learning tasks with the aim of improving each agent's performance without disclosing any data. This requires an organization to trust another organization with the local execution of machine learning algorithm on the data residing in the premises of the latter. Since the computation is defined by one party, the algorithm's owner, and the data is owned by another party that also runs the computation, there might exist an inherent trust problem: how to ensure the correct computation is performed and that the reported results are the corresponding outcome of that computation. So what do we aim to achieve? We propose a framework which allows delegation of a computation to the data owner while ensuring the provenance of a computation process, and which supports the sharing and trading of the computation results in a controllable and secure manner. What is the scope of this work? This work is a joint collaboration between FBK and IBM within the INFINITECH project. FBK has developed a fraud detection federated learning algorithm run by a consortium of organizations on their own nodes and on their own data, while sharing the intermediate learning results with each other to achieve higher precision. IBM provides a blockchain-based secure execution framework for the distributed fraud algorithm execution, recording all the meta information regarding the execution and recording the shared intermediate results on a transparent, immutable, and verifiable ledger. At the end of execution, a completed model can be shared as tradable asset on a blockchain-based data marketplace also developed by IBM. The blockchain-based data marketplace provides a tradable assets catalog where consumer organizations can search for available assets and gain access by paying for those assets using digital tokens. In our demo, we will show the whole flow starting from federated learning algorithm development and publishing of algorithm image, to running the image by multiple organizations while sharing the intermediate results on chain, to completed model creation and publishing on the marketplace, and finally the purchasing of this model by external organization. First, some information on the demonstration environment. For the demonstration purposes, we have a Dockerized deployment of Fabric blockchain on a Linux machine, along with an API service client application implemented in Node.js. This client application wraps Fabric JavaScript SDK and provides RESTful API services for interaction with chain codes deployed on the blockchain network. We have a local Docker image registry for the storage of the algorithm image, but of course any other image registry can be used to publish images. During the demonstration, Docker containers built from the federated learning algorithm image are instantiated and run locally, but they can be run in a totally distributed manner, as Kubernetes pods, for example. Let's go over the steps of the scenario. First, the algorithm developer builds a Docker image for the federated learning algorithm. The developer publishes the image to a Docker image repository. Then he registers the image metadata on chain, interacting with the blockchain platform through API services client. At the next stage, the consortium of organizations that run this federated learning algorithm starts the distributed learning process. The admin runs the script initializing the learning process. The image metadata record is read from the ledger. The Docker image based on the image metadata is pulled from the image registry. The distributed learning process is initialized by pulling appropriate configuration information of participating organizations and their respective computation nodes and creating the learning process record on the chain. Then the learning process orchestrator script needs to run the first iteration of a computation on all nodes. It creates execution record for each computation on the chain. It creates private and public keys for each computation task and stores the public key in the execution record on chain. The private key will be passed in the next step to the created Docker execution container, where it will be used at the end of a computation to sign the result. In step 8, the orchestrator script creates a Docker container for each node running the computation from a federated learning image, it passes the private key as initialization to this container, and this container is executed on the organizational node using as input the organizational data. At the end of this execution step, the results of the computation, signed with the container private key, update the execution record created for this container. The chain code writing the result on the ledger checks that signed result matches the public key stored in the execution record, thus checking that the result is indeed reported by the correct execution entity. Steps 7, 8, and 9 are repeated in a loop until each node finishes its calculation. At each iteration, an execution record is created per node. A containerized execution of the image starts on the node pulling organizational data. Previous results by their nodes are pulled from blockchain execution records of previous iterations. Computation is executed, and completed assigned result is published on the chain. At the end of the computation of all nodes, the learning process status is updated to completed, and the final outcome of computation, a completed model which can be traded with external organization, is stored on the blockchain data marketplace. The tradable asset record on the chain contains metadata related to the asset creation process. For a federated learning model, this information would be, for example, an algorithm image the model was created from, the learning process, the model is the outcome of the owner organizations, and the price. This information is searchable and can be used by organizations to search for and find interesting assets for consumption. The record of asset also contains the model binary itself, which can be traded with external organizations. The red arrows represent such an external organization's actions when working with the data marketplace. It can search for appropriate assets by querying the blockchain data marketplace. It can then request access to the chosen assets. If an organization has enough funds on its token account, the access request would be created and approved, otherwise not. When an organization tries to access the asset, the chain code verifies whether an approved access request for this organization and this asset exists, and access is either granted or denied accordingly. We have just gone through the whole scenario for federated learning process execution and asset trading. Let's dive deeper into each part and see the execution of each step. The first part will focus on algorithm image creation and pushing on-chain. The fraud algorithm developer creates a Python algorithm for the federated learning, naming this algorithm federated learning PY. The developer then creates a Docker file describing how to build the Docker container wrapping this algorithm. The Docker file includes instructions on the mandatory Python prerequisite libraries needed for the algorithm execution and the main entry point to run the Python application. The Docker image is built by running the docker build command using the Docker file. The created image is tagged and pushed to Docker repository. The image metadata, including the hash of a Docker image, is written on the blockchain by using the API service RESTful endpoint. Let's see the demo of a sequence of steps. What you can see here is my Linux environment, where I'm going to build the Docker image from a federated learning Python algorithm and going to push the image to my local Docker repository. Then I'm going to connect to my locally running API service Fabric client to push the image metadata to the blockchain ledger. Here you can see the Docker file, which is basically a set of instructions how to build the image. The Docker file basically contains instructions to bring in Python dependencies in the requirements file, create the working directory with the fraud detection algorithm application, and run the application. The fraud detection algorithm in itself is a computation which is going to run the container we'll create. It will read previous run results from chain, compute current run results, and publish them on chain. Here you can see the main method, which basically executes this compute result function, which is a step-by-step decision the computation is taking, whether to just perform a computation, read the previous computation results from chain, or publish its current estimators on chain by signing them.
with the private key. We'll see this later. So basically, this is the federated learning algorithm. This is the Docker file for building an image from this algorithm. And we are going to create the image by running the build image sh script, which basically runs docker build command with the Docker file we have seen. So let's build the image. The name of the image would be federated fraud. Now the image is created, and we are going to tag it and push it to the local Docker image registry. Now we tag the image. Now let's push it into Docker repository. We are pushing the image to our local Docker repository. Now the image have been pushed to the image repository. Let's take a look at the image we have created. Here is the federated fraud image we have created, and this is the image ID. This is the image information. One of the important parameters is the repo digest hash here. Since this is the hash, we're going to extract and save on the blockchain for verification purposes. So this is the SHA-256 hash. Please remember it for later. The last step in the image flow is creating the image metadata record on blockchain. For that, we are going to execute the publish image script, which basically runs this Python application. It receives the ID of the image which metadata record we'd like to create. It pulls the image from the image repository by the given ID. It calculates the hash we have just seen. It connects to the API services using the RESTful endpoint it provides, and it will write the hash along with other image metadata into the image record on blockchain. So let's run the script. So we're publishing the image metadata, and as you can see, this is the content of a metadata record, which is going to be published on blockchain. This is the hash we have seen, which the script have pulled from Docker image repository and is storing on the blockchain image metadata record. Let's take a look at the image we have published. I'm going to connect to the API service using Postman. This is my Postman, which is connected to the API session environment running on the Linux machine. You can see here the URL of the API session, and already logged in with the appropriate blockchain user, was certified and got authentication token, which I'm going to use in all my consequent requests. So let's execute the get Docker image operation. This is the API service endpoint for getting an image record from blockchain. So as you can see, we retrieved the image metadata record from blockchain. It contains different information regarding the ID of the image, the asset type saved on the blockchain. As you can see here, the Docker image ID, this is the hash I've shown you previously.
After the prod federated learning image is pushed to the image repository and the image record is published on chain, we can use the image to run the distributed learning process by a consortium of organizations on their organizational nodes, each using their organizational data. Let's now dive into this process. One of the authorized organizational user initializes the prod federated learning process by executing a run demo script. This script executes Python application, which pulls the execution environment configuration information, such as which organizations participate in the learning process and which organizational nodes are to be used to run the computation task, from a JSON file. The script pulls the image metadata record from blockchain using API service, pulls the corresponding image from the image repository, verifies that the hash of the image is the same as stored in the blockchain image record, and initializes the learning process. A learning process record containing all the metadata pertaining to the execution, the image being executed, and the participant organizations, as well as additional information, is created on the ledger. For each of the computational nodes, a private public key is generated for signing and verifying authenticity of computational results. For each computational task, an execution record with the execution metadata, such as node information and the public key, is written on blockchain, and a Docker container executing the computation is started on each node, while the corresponding private key is passed to the instantiation of this container. Each container runs the computation and publishes the iteration's results on blockchain, signed with a private key. The iteration steps 6, 7, and 8 are repeated. Execution records for the new computational task are created on chain. Docker containers executing the computations are started on the nodes. They read previous run results from blockchain, perform their computation, and publish the results on blockchain. This continues until the overall computation is completed. The learning task record is updated with the completed status, and the final outcome of the computation, that is the final model, is published on chain as tradable asset.
Let's take a look at the run demo script, initialize the federated learning process, and monitor the results of execution. This is a script, as you can see here on the screen. It runs the demo PY Python application. This application receives configuration. This application receives configuration of the learning process either through arguments, as we can see here, or through a configuration file. This configuration includes the learning algorithm image to execute, the image repository, the consortium of organizations and their organizational nodes, credentials for API session, etc. Then this application reads the image metadata record from blockchain using the API session, as we can see here. So it fetches the image metadata from blockchain. It creates a learning process record. It pushes this record to blockchain, and it parses the configuration, and it initiates containerized execution of a specified image on each of the configured nodes, keeping track of the current iterations until the process is completed and the final model is created. So I'm going to execute the script, which will initialize the learning process. This is the script we have just seen, which runs the demo PY Python application. I pass the configuration information inside the script's arguments. I pass the URL to the Docker image repository, the tag of the algorithm image I would like to execute inside my learning process, and the list of organizations and mapping of the organizational nodes on which I'm going to perform the computation. So let's execute the script. During the runtime of the script, it will parse the configuration, and it will start containerized execution of the algorithm image, and it will take a couple of iterations. It's a long iterative process. Computation tasks are run in parallel on all the configured nodes. once the first iteration completes, the second iteration is initialized, and so on and so forth, until each and every one of the nodes decides it has reached completion of a learning task. We can see here it publishes results to the execution records. So each time a computational task is run on a particular node, it will write the execution information onto blockchain. While the learning process is running, let's take a look at the artifacts being created on chain. As I explained previously, once the learning process is initialized, the learning process record is created. So let's fetch this record and see what it contains. I'm going to use Postman to connect to the API service, which will invoke a blockchain transaction to read the learning process record from the ledger. So this is my Postman environment. What I would like to do is run a query which will fetch all the learning processes for a particular image tag. The image we're running is federated fraud. So let's execute this query. And I can see that I have only one learning process instance. Those are consortium of organizations running this learning process. The status is in progress. Currently, it's on 4th iteration. So let's fetch information of execution records of this learning process. I'm going to run get learning process record for my learning process. So we see all the information. So now let's get all the execution records for my learning process. So I can see here all execution records for my learning process. The task ID contains the name of the learning process, the number of iteration, organization of nodes which perform this computational task, and also timestamp. You can see here the public key which was written on chain while initializing this container task. The private key was passed into initialization of this container task, and then it was used to sign results of execution task. So, for example, here we see the computed estimators by this computational task, and then the results being written on chain. It's been signed with the private key of this container task, and the chain code verifies that this private key, which was used to sign the results, is the same as the public key, which we passed to this container during its initialization. So I'm basically making sure that the entity which is writing the result is the same entity which I initialized to perform the computation. Eventually, when the learning process is complete and all the iterations have successfully terminated, we can see that the status of the learning process was updated to completed. We see the final number of iterations. So this learning process consisted of 13 iterations. We can also take a look at particular iterations, computations of particular iteration for this learning process. Let's say iteration number 11. This is my learning process ID, so I can query the blockchain and receive a list of execution records of this iteration from different nodes. Here we see org1 node 0, org1 node 1, org1 node 2, node 3, node 4. We can see that the status of this iteration, results, and assigned results. So we can see the provenance of all the steps in the learning process. And finally, if I go back to my terminal where I execute the learning process script, I can see the output of this script. So at the last steps, I can see that the simulation terminated after all the nodes completed their iterations, their calculations, and I can see that we've seen already this learning process record being updated to status completed and with the final number of iterations. And we can also see that a completed model is generated and the model asset is stored on chain. And we'll deep dive into the tradable asset and what we can do with it later.
Finally, we reach a step when our federated learning process is completed and the model generated as a result is published in the data marketplace to be traded with external organizations. We mean by external any organization which is not the model owner but participated in the model creation. The data marketplace offers an asset catalog with asset access governance. Let's see next how an external organization can search the data catalog and purchase from our model. The external organization searches the data marketplace asset catalog for a certain model. Let's assume it searches for fraud detection models which were created as a result of a federated fraud image execution. As external organization, I search for the relevant assets and get their metadata, but not the actual content of asset. If I'm satisfied with the model I would like to purchase, I'm familiar with the algorithm which has generated it, and I trust the organizations which perform the computation, I request access to this model. The access request record is written on chain. A cross-chain code invocation of the ERC tokenization chain code verifies that I have enough tokens in my account to pay for the model. The price of the model is part of the asset record in the marketplace catalog. If my balance is sufficient, the data marketplace chain code invokes the tokenization chain code to transfer the proper amount of tokens to the model owner's account, and the access request record is updated to state granted. As the next step, I would try to fetch the whole records for the model, including its binary, and since I have an approved access request for this asset, I will be granted access.
Let's see what tradable asset was created as a result of our learning process execution and how we can use the data marketplace catalog to search for it in traded with external organization. So currently I'm logged in as org1 user. If you remember, org1 was one of the organizations which participated in the federated learning and therefore one of the owners of a model which was created as outcome of this learning process. So let's explore a bit the tradable asset record which was created on the ledger at the end of the learning process. I'm going to execute a query which will fetch all assets created as a result of a federated fraud algorithm execution. So let's perform a query. As you can see, there is just one asset like this. This is the asset ID, the asset type. We have owning organizations. We have the price of this asset in tokens. It's 500 tokens. And we have some additional information, such as the image this asset was based on and the learning process ID. Please note the metadata we see does not include the actual asset object. In our case, this is the model binary. All queries and searches in the asset catalog return only the metadata of the asset and not the asset itself. In order to access the actual asset object, the binary or any other type of a document representing the content of asset, you need to be either the asset owner or have an approved access request for this asset and perform a get for asset by ID, not just a general query. General query will only return the metadata of asset. So let's demonstrate that. Currently I'm logged in as a member of org1 organization. So I'm one of organizations which own the asset and can access the asset object. So I will run a get operation on the asset and see if I can also access this object. So let's copy the asset ID and perform the get operation. I'm just pasting the asset ID. As you can see, I can fetch the whole content of the asset. In this demo, since the model is relatively small, we save the whole object on chain. But in general, we can store the asset object off chain on cloud object storage, for example, and save here just the URL and the hash of the object on chain. So the hash can be used to verify the authenticity of the object after it's fetched from the specified URL. Okay, now let me log in as a member of an external organization which did not participate in the learning process and did not create the model, therefore is not the asset owner. Currently, I am logging in as org-free user. So now let's try to run the same query as we did before for searching the data catalog for asset, and afterward try to read the entire asset. So let's query all the assets. As you can see, it returns the same information as previously. So now I found the asset I'm interested in, and so I'm trying to read the full data of asset by executing the get query with this ID. So as you can see, I get an error since the invoking organization is not the asset owner and does not have approved access request for this asset. So as you can see, external organization can search and find information on the asset metadata using the catalog, but it is not able to fully access the asset without approved access request. So what is required for external organization to be able to access the asset? It needs to create access request, and assuming it has enough tokens in its account to pay for the asset, those tokens will be transferred to the owner org account, and an access request in state approved will be created for this organization and that asset. I have already created some token accounts and minted tokens into them. Let's see the state of these organizational token accounts. For this, I'm going to use Fabric CLI, which can connect to one of the peers and submit transactions directly without the help of Fabric client application. So here I am connecting to Docker CLI. Now I'm going to execute the query directly. I'll just explain the content of a query. I'm invoking the chain code on default channel. This is the name of a chain code. It's tokenization chain code. I'm invoking the function balance off for org free. So this is the answer. Currently org free have 720 tokens. Let's see also balance for organizations 1 and 2. So org 1 have 1,720 tokens. And organization 2 have 560. So let's invoke the request access operation when we're logged in as org-free user. So I'm pasting the asset ID. I'm creating the access request for. So the return result was successful. Let's check the current balance of organizational accounts as we have done previously. So I'm executing the same CLI query. I'm checking the balance of org free, which was supposed to pay 500 tokens for the model access. And we can see that previously the token balance of this organization was 720 tokens, and now it's 220. Let's also check the balance of org1, the owner of the asset. And if you remember, it was 1,720, so now it's the current balance. We can also check and see that a new access request for our model was created for org free. So let's execute a query to get all access requests for org-free. We can see the new access request for our asset, and the status of this access request is granted. There is also additional information here, such as when this access request was submitted, when it was created on the ledger, etc. Last but not least, let's try to access the model asset now. I will copy the asset ID, and I will try to access the tradable asset now as org-free. So I'm logged in as org-free, and as you remember, we previously couldn't access this asset. And as you can see now, since now org-free has approved access request for this asset, it can access the model and use the model for its purposes.
To sum up, we have presented a blockchain-based secure execution environment and data marketplace for fraud detection federated learning. Possible extensions to our work. The same framework can be used to support the execution of various algorithms as long as they can be represented and packaged as a computational task and Docker image. We have demonstrated cross-chain code invocation and usage of previously developed ERC-based token smart contract inside the data marketplace. We are currently applying ERC-20 implementation for assets trading, but other token implementations, such as ERC-1155, could be deployed instead and used in the same manner. In addition, in our demo, we show simple functionalities of marketplace for the sake of illustrating the digital trading of learning models applying tokenization blockchain. This data marketplace can be extended to provide more functionalities, from richer querying capabilities to pluggable pricing models and advanced trading options, such as auctions and price negotiations.